Let's talk about electrostatics, also known as static electricity. Probably that's how you know it. That's how you've talked about it. Sometimes we just use the word static to mean this. Actually, the word static really doesn't have anything to do with electricity. We're also going to talk about something called Coulomb's law today. So let's go ahead and get into electrostatics. So first of all, what are we talking about when we talk about electrostatics? Well, electrostatics is simply the study of electrical charges. This is important, that can be collected and held in one place. Again, we also refer to this as static electricity, electrostatics. You might notice that the word static is common to these two. The reason for that is, unlike what most people tend to think, the word static actually doesn't have anything to do with electricity itself. Static just means still or stationary. If something is stationary, it's not moving. So we refer to static electricity because this is about electrical charges that don't move. They stay in one place. And it's important to note that this is not the same thing as the electricity in your wall outlets, right? The electricity that comes out of a wall outlet when you plug in a TV or your computer or your phone, that electricity is flowing by definition. That current is charge that flows. It is not stationary, so it's not static electricity. So now you might be like, well, Mr. Valls, why are we doing this if this is not the electricity that comes out of the wall? Because like that's the most important kind of electricity, right? Yes, and that's the electricity that I'm recording this video a week after the huge snowpocalypse of 2021. If you're watching it later down the road, last week it's the electricity coming out of the wall that we didn't have, and that was the biggest problem. But in order to understand that electricity, in order to understand current, we have to understand the foundations of electrostatics first, because in order to get current to flow, we actually have to build up charge in one place first. So let's talk about electrostatics. So first of all, what are some examples of static electricity? Well, you've seen lots and lots of them. If you comb your hair, especially if it's a dry day, sometimes you might see something like this. Your hair tends to stand on end. Well, that's the result of static electricity. You're charging your hair actually with the comb. Clothes in the dryer, if you don't have a bounce sheet or a static sheet in there, sometimes those clothes cling together or they can cling to you. That's a result of static electricity. Sometimes we use the word, my clothes are staticky. That just means that they're electrically charged and they're sticking to each other, they're clinging to each other. Balloons, I'm going to use the example, I'll show you an example later on of sticking a balloon on a wall. That's an example of static electricity. You might have done that on your own. Maybe you've rubbed a balloon on your hair and seen your hair stand up. That's an example of static electricity. Lightning is actually a humongous example of static electricity. We're simply building up two different charges in the cloud versus in the ground. And when those charges get large enough, there's a humongous discharge that we call a lightning bolt. So let's talk about what this all is. First of all, there are two kinds of charge, and you might already know this. There is positive and there's negative charge. Maybe you should write that down if you don't know that, but I bet you already know that from chemistry. There's positives and negatives. And you probably also know from chemistry that where do those charges come from? Well, they come from the parts of an atom that you already know about. You should already know that protons are positive, electrons are negative, and neutrons are not negative, neutrons are neutral, which means neutrons, they're sitting there, but they don't participate in the electrical process. They don't participate in electrostatic charges. So here's a model of an atom. We've got electrons on the outside. They're theoretically moving around the outside. There's a lot more to that we won't get into. We've got protons and neutrons on the inside. Now it's important to note, and I'll get to this more in a minute, that protons and neutrons are in the nucleus, which is very tightly bound. You can see that these molecules are very close together. The electrons are very far apart. As a matter of fact, the electrons are even farther apart, much farther apart than this picture shows here. So the protons and neutrons are in the nucleus. That's going to be important in just a second, and I'll come back to it then. So we got electrons and we got protons. Those are the main two parts that participate in electricity. The electrons are the negatives, the protons are the positives, and they're in the nucleus. So if I talked about all those objects getting charged, well, how does that happen? How do objects become charged? Well, there's a larger story to that I'll talk about more. I'll go into more detail in a minute. But basically what happens in one way or another is that charged objects are either going to gain or lose electrons. Electrons. Hint, hint. This is called electricity because it's about electrons. It's not about protons and neutrons. This is so important. You need to write this down. Protons and neutrons are not transferred between objects in electricity. And the reason is because they are quote unquote locked in the nucleus, which is what we just said a minute ago. Now, in the nucleus, we're going to talk about this more later when we get to nuclear energy. But basically what you need to know is that there's a force between protons and neutrons in the nucleus called the strong nuclear force that binds them together. It is strong. It is very strong. So strong that electricity can't pull them apart. We got to have a nuclear reaction to pull them apart. So for our purposes today, the strong nuclear force is like a glue in the nucleus that holds that nucleus together and everything in it. The protons are not coming out. They don't get transferred. The electrons, on the other hand, they are held in the nucleus by the electrostatic force because negatives are attracted to positives. You might know that, but we'll talk about that in a minute. But they're not held near as tightly. It's pretty tight, but they're not held near as tightly. The ones especially on the outside are going to participate in the electrostatic process, in the electrical process, because they can move a little bit easier. All right, so those are the forces going on, and the point is you need to focus on this, the fact that there's this glue in the nucleus called the strong nuclear force that means we're not going to mess with protons. Now, they do participate in the electrical process because they're charged, but they don't move. They don't move from place to place. That's the important part. They don't move from atom to atom or from object to object. They're locked. So, if an object gains electrons, remember it's all about electrons. An object is either going to gain electrons or lose electrons. If it gains electrons, it becomes negative, and if it loses electrons, it becomes positive. Again, no gain or loss of any protons or neutrons. So we're gaining electrons, negative, losing electrons, positive. So for instance, I have these two hypothetical atoms. They could represent just objects as well. But right now you can see that they are both neutral, and the reason they're neutral is not because there are no charges, but because they have equal numbers of electrons and protons, 6 electrons, 6 protons for each. So if for some reason the one on the left loses an electron to the one on the right, then that would make the one on the left positive, not because it has gained any protons. Notice the number of protons stayed the same. It's simply lost in electrons. So now when we compare the number of electrons and protons, the protons sort of went out. And so overall, we're going to say that this object or this atom is overall positive because it has lost electrons. It's lost the negative charge. Whereas the one on the right, it has gained a negative charge. And so it's overall negative now. It's negative because it has 7 electrons and 6 protons. Once again, number of protons didn't change. We didn't gain or lose any protons. All we did is gain some negative charge. So it's all about the negative charges again. That's why it's called electricity. It's about electrons. You either gain electrons and become negative, or you lose electrons and become positive. So there's this really quick table right here that basically says the same thing. In the middle, the choices that go in these are basically greater than, equal to, greater than, less than, or equal to. And over here, to determine what happened to make it positive or negative, we had to know either electrons were gained or lost. So see if you can fill in these blanks and these blanks right here. Pause the video and see what you can put in there. All right, so hopefully you came up with the fact that in a neutral object, the number of protons and electrons are exactly equal to each other. Neither one of them wins out. That's why it's neutral. Once again, it does not mean there are no charges. There are protons, there are electrons, but they're equal. In a positive object, the number of protons is greater than the number of electrons. There are more protons than electrons, but check it out. That doesn't mean that protons were gained. That right there is going to be, I promise you, that's going to be an answer choice on a quiz. And a lot of people are going to pick it because it makes sense, right? Well, if I gain protons, it's got to be positive, right? Not possible. Electrons were lost in order to become positive. And in a negative object, the number of protons are less than the number of electrons. How are the number of electrons greater? That's because electrons were gained. Once again, for like the fifth time, there is no net transfer of protons or neutrons. They're locked in the nucleus because of that strong nuclear force.